Good morning or good afternoon, everyone, depending on where you are joining us from, and welcome to today's webinar. My name is Simon Thorpe from the Business Review, and I'll be the moderator for today's session. It's our great pleasure to have VTT with us today, who are going to be discussing state-of-the-art fluid bed thermal conversions for energy and biofuels. Today's main guest speaker is Dr. Jussi Manninen, who is a principal scientist. And we're also joined by Dr. Jani Leto, who is a principal scientist, and Mr. Esa Kokela, who is a research manager. I'd like to take this opportunity to remind the audience that you could submit questions using the Q&A tool at the right-hand side of the screen, and you can do this at any point throughout the presentation. We're then going to allocate around 10 to 15 minutes to try and answer any questions and thoughts. So without further ado, please allow me to welcome Dr. Jussi Manninen. Over to you.
Thank you, Simon, for your kind introduction. Good morning, good afternoon, good evening, everybody. Let me first start with the introduction of the esteemed colleagues that I have with me here. So Dr. Jani Leto and Mr. Esa Kokela, and I will be doing most of the talking now, but they will be answering all the questions that you will have in the end of this session. And let me just start with a few words about where we come from. So VTT is the Technical Research Center of Finland, and we are an applied research organization. And on the left you can see some of the main figures that we have. We have almost 3,000 experts employed. We do applied research with the highly unique research and testing infrastructure that you will see parts of it in my presentation. And we work in 3 business areas: in knowledge-intensive products and services, smart industry and energy systems, and on solutions for natural resources and environment. And all the presenters of today's presentation are from the solutions for natural resources and environment business area, where all our bioenergy and biofuels activities reside. And we work directly with companies with the aim of providing them with new business opportunities through innovations. And we also work with the public bodies such as government to give them guidance for political decision making. And we are also, of course, being a Finnish organization, we have a special place in our heart for Finland. So today's presentation is about fluid bed platform. And just a reminder of some of the learning objectives for today. So we hope we can convey to you all how cutting-edge R&D and process piloting can actually help to achieve your goals of using residues to generate new revenue streams for your industries. We'll explain to you why Fluidised-bed itself is an excellent platform for efficient conversion, be it combustion, pyrolysis, or gasification. We also want to show you how it makes sense to integrate processes with each other to maximize the synergies available for both energy material-wise and also for cutting capital costs. And for each one of the topics for gasification, combustion, and pyrolysis, we'll be showing you some demonstration cases to see where these technologies have been applied in practice. Out of the less than 3,000 people at VTT, around 100 professionals work around the Fluidised-bed technologies. And the technologies, we are working on combustion, gasification, pyrolysis, and also on catalytic processes. And really all these 4 areas share the common heart, the Fluidised-bed, but of course the main differences are related to the atmosphere and the temperature and the technical issues regarding the process itself. But something that really defines us in all of these applications are that we look at clever integrations between processes in order to save energy and capital. We work very closely with the industrial partners all the way from the start of the innovation cycle, and we also have excellent experimental capabilities to scale up these technologies towards demonstration and industrial practice. And just to give you an idea of the versatility of the Fluidised-bed platform itself, we can see here that that we can apply it into combustion for generation of power, heat and cooling, for pyrolysis to produce fuel oil, and also for more advanced oil products. And actually in our case, we have integrated the pyrolysis technology with fluidised-bed, and you will see that bit later in the presentation. And thirdly, gasification, where you can take the synthesis gas into fuels and chemicals, or used as a fuel gas in boilers, kilns, and engines. So that shows the versatility of the platform itself. And what we'll now go through are 3 separate cases. So I will start with gasification, which is really about converting, in our case, solid biomass to gas. So here we can see a schematics of gasification. Basically what gasification is turning carbon-containing material into gas, which contains carbon monoxide, hydrogen, and some carbon dioxide. It takes place at high temperatures, you can see on the slide, in the presence of air or oxygen and or steam. And traditionally, you can use this on a very wide feedstock basis. So that traditionally, it has been utilized for coal and for oil. But what we are going to talk today are the raw materials on the left, on the bottom left of the picture, which are biomass, and we'll also talk about waste. Once we actually have gasified the products or the feedstock into the 3 constituents, the CO, H2, and CO2, the gas needs to be cleaned before it can be actually taken on for further processing. So the 2 main routes are really to the upper right-hand corner, the syngas route, into fuels and chemicals, and the other route is to utilize the gas as a fuel gas in kilns, in boilers, gas turbines, engines, and so on. And really the amount of the cleaning is then dependent on the end requirements of these 2 routes. If we delve a bit deeper in the process itself, you can say that there are 2 ways of gasification. The traditional method, or the traditional way, is to have a high temperature entrained flow gasifier and then produce synthesis gas from it. When it comes to biomass, which is in our focus today, there is a problem related to handling and feeding of the biomass. So by itself, and as such, the technology is not very well suited for biomass gasification. The route that we have taken is to have a gasifier, fluidised-bed gasifier operating at a slightly lower temperature, which is well suited for having biomass as a feed. And the challenge then lies here in the conditioning or reforming of the gas to improve its quality before it can be taken for further processing. And the presentation that I will be showing will be then concentrating on the bottom part of the presentation, which is the fluidised-bed gasification of biomass. Additional item to bear in mind is that the main steps of producing synthesis gas from biomass, we start with biomass drying. So the biomass needs to be dried before the gasification. Of course, we need to gasify it and then reform the gas further to improve its quality. And then clean the gas. And these first 3 steps are the ones that have required a lot of research and development in order to be able to produce clean synthesis gas from biomass. The next steps in the process are then to condition the gas and to have gas synthesis or upgrading into fuels and chemicals. And these two last steps are well-proven technology. They have already been utilized for decades with gasification of coal, for example, and they're more or less off-the-shelf processes that can be purchased from vendors. We have been involved with gasification research for quite a while, and in the heart of all this development is the process development unit, which we have at VTT, which has a 0.5 megawatt thermal effect. And it is a pressurized fluidized-bed gasifier that can be operated either with air or with oxygen, depending on the application that we are looking at. And it comes with an advanced filter for high-temperature cleaning of the gas, catalytic reformer unit for reformation of the gas cooler, and then a possibility of taking the syngas for further processing or synthesis. And this is a platform that we can use to develop and test various types of gasification processes. The example of gasifications that I will be talking today involves biofuel production from biomass and its integration with pulp and paper industry. This is a concept that we developed with some of our industrial partners about 10 years ago. And the idea of integration of this biofuel production with the pulp and paper industry comes from two main reasons. First of all, the pulp and paper production has a working logistics for biomass. They are already controlling vast amounts of biomass, and they have logistics to bring it into their factories. So there is an integration synergy with the biomass logistics. The second integration benefit comes from the fact that the synthesis of the syngas into Fischer-Tropsch liquids that then can be converted into diesel produces high temperature waste heat. And this waste heat can be nicely integrated with the pulp and paper mill in order to save fuel at the power plant of the mill. So the mill benefits from this additional heat source. Also, some of the low temperature heat that is usually available at the pulp and paper mill can be utilized back at the gasification process for the biomass drying. So it gives also a possibility of utilizing waste heat that is otherwise needs to be discarded into the environment. And this concept has been piloted, and I will show in the next slides some examples from industrial demonstration of this concept. This took place a couple of years ago at Varkaus mill in Finland, which is in eastern part of Finland, and there was a joint consortium by a Finnish oil company, Neste Oil, and a Finnish pulp and paper company, Stora Enso. And what they had, they built a demonstration unit in Stora Enso Varkaus mill with the idea of converting forest biomass into liquid transportation fuels. VTT's role was to carry out the research and development activities in the areas of gasification, gas filtration, and the reforming of tars and hydrocarbon gases on the way to being synthesis gas. And of course, with our long experience, we also brought expertise regarding gasification and gas cleaning. From technical point of view, the demonstration went really well. There was a long periods of time where the gasification was operated continuously at a very high availability. This demonstration did not result yet into an industrial plant being built, but with the experience from this demonstration, we have all the possibilities of actually designing the first commercial size plant. And as an example of how good the technology, the gasification technology is, the gasifier itself is still operating at the mill and producing fuel gas for the lime kiln of the pulp mill. One of the questions that pops in mind when we are looking at these new business opportunities are the economics. How profitable is it to produce liquid biofuels from forest biomass? What we have recently done is we carried out techno-economic calculations of 20 plant concepts where we were looking at large-scale production or large-scale gasification of biomass into 4 different liquid transportation fuels: methanol, dimethyl ether, Fischer-Tropsch liquids, and then gasoline. And you can download we will send a link for all of you so you can download the document after this presentation. And here are some of the results. What you can see on the top part is some of the economic data we used as assumptions in these calculations. We also assume that the economic figures do not involve any investment support, no CO2 credits, no tax assumptions, so in a way, fair game. And what we can see from here is that the production capacity, the 300 megawatts, relates to around 200,000 tons production of methanol or dimethyl ether, or 120,000 tons of Fischer-Tropsch liquids and gasoline. And what we can see here is that the break-even point can be achieved when the crude oil price is around $130 per barrel. That's when this starts becoming profitable. What we can also see from this slide is that if you compare the bars on the left with the bars in the center, you can see the difference between having a heat integration of the process. So on the left, there's assumption that the waste heat is not sold as a heat, but it actually goes into power production, whereas in the center, part of the heat can be also sold as heat to the surrounding community. And again, the difference between the economics between case 2 and case 3, so the difference of how advanced or how efficient the production technology is. Another opportunity related to gasification is to gasify waste and co-fire it in existing boilers. And that can actually provide a quite cost-efficient way of reducing CO2 emissions in existing boilers. And we have been actively involved in that path too, starting from lab characterization and development bench scale for these type of concepts, moving into pilot scale of these waste to energy concepts, and eventually ending up with 2 commercial examples. The first one being installed at Corenso in the early 2000s, where the feed is plastic reject, and that is gasified. And the second one from 2 years back at Lahti Energia in Finland, where solid waste is being gasified. And these are existing plants operating at this moment. So to sum up our approach to gasification, so what we can offer is excellent know-how on the fuel chemistry and the gasification processes itself, unique test facilities all the way from laboratory to pilot scale. We also have very good mathematical modeling tools for process modeling, both steady state and CFD, which is computational fluid dynamics. We have a proven track record, as you've seen, on industrial development and industrial demonstrations. And we also own some IPR on gasification technologies themselves. So really, with the gasification, that gives the possibility of upgrading a wide range of cheap and low-quality feedstock into valuable products and intermediates. And the two examples I've shown is the industrial-scale production of superior quality liquid biofuels and the cost-effective way to recover energy and also from materials from waste, and at the same time reduce CO2 emissions in existing power plants. And as with any technology, there are further development needs. In the large scale, we still need to work on the efficiency to bring the cost of production down, but also there are exciting possibilities related to smaller scale gasification processes and the possibilities it gives to integration into smaller units and the possibilities of having distributed production of intermediates and then having a centralized upgrading facility. I will now move on to the second case, which is combustion, and I will be concentrating on Circuline's fluidized-bed combustion for high efficiency and low emission energy production. The fluidized-bed combustion technology has many advantages, and it actually started with the idea of having combustion technology that can handle difficult fuels. So fuel flexibility is one of the defining features of fluidized-bed combustion technology. So it can tolerate high moisture, high ash, and high sulfur fuels, and mixtures of different fuels. It also provides low emissions, both sulfur emissions with the possibility of injecting limestone into the bed itself, and low NOx emissions because of the low and uniform combustion temperature in the combustion chamber. As I'll show you, it also provides excellent scalability all the way from very small district heating size units of 1 megawatt all the way up to utility scale power production. It also now can compete efficiency-wise with the large pulverized coal plants due to advances in technology which has allowed us to move into supercritical steam parameters, and we can achieve over 40% electricity efficiency in the power plants. And also it is quite well suited for oxygen combustion, which is then a route to carbon capture and storage, as I will show you a bit later in this presentation. So on this next slide, you can see actually the quite remarkable transformation that has taken place in the last 2 decades when you look at the size of the plants that have been able to be built with the fluidized-bed technology. And really one of the most important milestones is the one which is located in 2009, which is the first supercritical once-through circularized fluidized-bed boiler being built in Poland at Lagiza, which is now operating and has actually operated very well. And with the improved efficiency has really given a remarkable reduction in both in CO2 emissions due to the high efficiency. And now plants are being built that are even larger than that, and plans exist for even larger plants, which I show here on the green, as we are trying to approach 800 megawatt milestone in size-wise. Another, what you can see, the small bar in the middle is the start of the next generation, and that is the size of the current demonstration unit, which exists for the oxy-combustion plant, which is very well suited for carbon capture and storage. And with you can see the green asterisk on some of the bars, and those denote projects where VTT had a coordinating role in the research and development projects that eventually led into the investment and build of these boilers. And our first pilot was built in the mid-90s And then onwards, we have been a very active player in the development of circularized fluidized-bed combustion. Of course, one of the goals is to reduce the CO2 emissions related to power production. And this slide here just illustrates the effect of the increased efficiency on the reduction of CO2 emissions. So if we look at the average European efficiency for power production, which lies at around 35% mark, as indicated on the slide, if we compare it with the best available CFB technology today, which is close to hitting 45% mark, that will translate into 21% reduction in specific CO2 emissions per amount of produced power. If one needs to go further down on that, then the fluidized-bed combustion offers the possibility of co-firing with biomass. And here we can see that if we were to substitute 20% of the coal with biomass, that would actually bring down the reduction almost to 40% from the original emissions. And as I will show you later on, further reductions from that are of course possible when we start capturing the CO2 from the combustion itself. All this scale up has not been easy, and it has involved a lot of research and development in order to understand what actually takes place in the combustion and in the boiler itself. And we have done a lot of work in bench scale in order to understand the phenomena behind the operation and design of the boiler. So how will it behave once we move into one-through boilers, how it will behave if we move into oxygen combustion. And from those phenomena-based models and bench scale, then moving on into pilot scale and incorporating all that knowledge into 1D submodels of the boiler. And eventually, during the scale-up, transferring all that knowledge, all that experimental information into the actual design software for the boilers in 3D format, and then actually being taken operational in utility scale. And this is in essence what we do when we do R&D and scale up in combustion. Just to give you an idea of the size and efficiency of these new boilers, here's an example of a power plant now being built in Korea, where you can see the size, over 1,000 megawatts of electricity. You can see some of the steam parameters, the efficiency, and also you can give an indication of the fuel flexibility. It can burn different types of coals, but also 5% share can be made of wood pellets. The next generation of fluidized-bed is what I'm going to present now. It's called FLEXI BURN concept, which is about trying to design a boiler that could be operated both in a normal mode using air as a combustion medium, but also using pure oxygen as a combustion medium in case we want to capture the CO2 from the boiler. And the reason for using pure oxygen, if we want to capture the CO2, is the fact that then we will have an atmosphere of CO2 and water, and just condensing the water from the flue gas, we will end up with pure CO2. And then this technology has been now scaled up in several steps. The first two steps took place at VTT. The 1 megawatt piloting scale step took place at Valmet in Canada, and there exists now a demonstration plant in Spain of 30 megawatts. So again, looking at combustion, so what can we do to help with your fluidised-bed combustion. We can be involved early on during the investment planning and design of the plant and the boiler. We can run techno-economical analysis on the economics. We can do fuel characterization services to see how the fuels will behave in the boiler. We can do extensive process and CFD modeling, also dynamic process modeling to look at the ramp ups and ramp downs. And especially when we are looking at one-through units, it will really pay off to combine the fuel characterization services with some dynamic modeling services to see how the boiler will actually behave. And of course, we have long experience in biomass co-firing concepts and on oxyfuel. So summarizing the benefits of the CFB technology, it has a fuel flexibility, low emissions. Now actually it's matured to utility scale with high efficiency, and it is well adaptable to oxyfuel in case one wants to employ carbon capture and storage in the boiler. And we have been a key research partner actually in these steps towards these high efficiency, large scale boilers. But again, there still lies some technical challenges, some development needs, which are listed here. The ever-increased need to increase efficiency and to come down in emissions, and also looking at even widening the fuel flexibility, now taking into account also from some agricultural residues. One of the issues that is really being topical in these days is how can we improve the dynamic performance, the load following capability of these units as the electricity system is moving into having more and more intermittent wind and solar energy production. And of course, one of the targets that we are already going towards is looking at zero CO2 with carbon capture and storage. Last but not least, let's move on to fast pyrolysis and see what the integrated bio production is all about. Here on the schematics, what we can see is pyrolysis, which really is about converting biomass at around 500 degrees temperature with a short residence time of 1 or 2 seconds into 3 main components: volatile organic components, non-condensable gases, and char. That takes place in the reactor on the left. So the gases, the non-condensable gases, the volatile, the pyrolyzed products, and then the char are then taken into cyclones where the char and sand are being separated. In the liquid recovery, we'll recover the oil, which typically amounts to about 60 to 75% of the biomass, and then the gases are then sent back to the combustor that provides the necessary heat for this pyrolysis reaction. And how the pyrolysis reaction actually gets its heat is a heat transfer sand that circulates between the combustor reactor and the cyclones. So fast pyrolysis of biomass actually has several advantages. First of all, the investment, from investment-wise, the pyrolysis plant is quite a moderate investment. And also the production cost for heating bio-oil, for example, are also quite competitive. From a logistics point of view, this concept allows the possibility to produce the bio-oil in distributed manner close to the biomass itself, and then transport the intermediate product, the bio-oil, into more centralized upgrading facility. And this upgrading facility can of course be a mineral oil refinery where this product could be blended into the mineral oil stream. And it also gives the potential for phased implementation into biorefining business. So one can start with the bio-oil and then adding more and more conversion steps, one can move into higher value products, which can be fuel for power production, it can be transportation fuels, or even chemicals. We have been working with two fast pyrolysis concepts. The first concept is the pyrolyzing biomass and producing bio-oil. And this is the concept that I will be concentrating for the rest of the presentation and showing the upscaling from pilot all the way to the industrial demonstration plant that we have currently in Finland. The other alternative for this path is to continue upgrading the bio-oil with hydrotreatment to remove water from it and upgrade the quality, and then end up with transportation fuels. The other path that we are working on in a bit smaller scale at the moment is the path where we actually have catalytic pyrolysis, which means that the bio-oil that comes out is already of higher quality than with the first concept. This gives the possibility of utilizing the bio-oil in stationary engines to produce electricity, or with a slightly, again with some more upgrading to produce transportation fuels or chemicals. Here the hydrotreatment does not need to be as severe as with the concept 1. And as with gasification and pyrolysis, we have very unique facilities available at VTT. So with the fast pyrolysis, we have a continuous process development unit, which is unique, which is capable of producing 300 kilos of biofuel oil or 100 kilos of catalytic bio-oil a day. And again, as with gasification, this is the development and test unit that we can use to develop our new concepts. What is unique to us is the way that we actually combine pyrolysis with combined heat and power production. So we actually combine the pyrolysis reactor with a fluidized-bed boiler, and that is the VTT concept. And there are basically two reasons for doing that. First of all, the fluidized-bed boiler itself will then provide the heat necessary for the sand for the pyrolysis process, and this way we do not need to invest into a separate combustion chamber that would provide the heat otherwise. So there will be some capital cost savings with this concept. The second idea behind this concept is to maximize the energy recovery from the pyrolysis process itself. So on top of getting the bio-oil, we can also now use the non-condensable gases and the char as an energy source in the power plant, thus reducing the need for external fuel needed at the power plant. So this is a unique concept to us, and we have taken it further into piloting and demonstration phases. So Valmet started developing their own process based on our concept, and they took it into their piloting unit, the 2 megawatt piloting unit. And here we can see on this slide, first the green bars show the quite rapid advancements in the operational availability of the piloting unit that took place during the piloting phase. So starting from virtually 0, going all the way up to 90+%. What we can see here on a smaller scale are how well actually our process development unit results coincide with the results that were achieved from the piloting unit, which shows that the scale-up has been successful, and we can also utilize the experience from our PDU in the scaling up. And this all now has been evolving into an industrial demonstration that takes place in Joensuu in Finland, where Fortum Power and Heat has installed a demonstration scale pyrolysis plant at their power plant, and then are actually using the bio-oil as a fuel there. And they want to now demonstrate the viability of the bio-oil as a replacement for fossil fuels in heat production. And really this, again, utilizes our patented process concept. So our approach, what we can offer when it comes to pyrolysis, is a unique process development unit, bio chemistry know-how, which is world-class, our computational capabilities when it comes to process modeling and computational fluid dynamics, and again, track record in industrial development and demonstration. And really with the pyrolysis, that provides the possibility of generating value-added products from forest residues. It has a quite moderate plant investment, so it gives the potential for phased implementation into biorefinery business itself. And also we have shown that the integrated concepts have cost benefits against standalone concepts. So the production cost will be lower with the integrated concept. And again, as with any technology, we are still working hard on bringing up the efficiency, bringing down the cost through better processes and better integrations within all the value chain from the feed material to products. In the future, what we're actually doing right now is moving our piloting facilities and upgrading our piloting facilities into a new location here in Helsinki region in Finland, and we hope to have our gasification and pyrolysis pilots operational there within the end of this year, and potentially in the future also bringing more chemical process chemistry and biomass fractionation pilots at the same site, so we can improve our services and provide better services all the way from raw material into products. So now, enough from me, and I would like to now hand over to Simon so he can introduce the poll question that we devised for you.
Brilliant. Thank you very much, Jussi. Okay, to the audience, now it's time for the poll of today's presentation. In a moment, a polling box will appear on your right-hand side of the screen with a polling question and a selection of answers. So if you can review and select the one that is relevant to yourself. So the poll question is, which of the presented new business opportunities did you find most interesting? First one, production of bio-oil by pyrolysis. Secondly, production of transportation fuels by gasification. Thirdly, high efficiency and fuel flexible production of power and heat by CFB. And finally, waste to energy and material recovery by gasification. Okay, so we've got about a minute while that poll is sort of open, so please do review and make the right selection. But Jussi, back to you. I mean, what's the idea behind this? Obviously, I guess it's for follow-up as well, and interesting to understand what's important for the audience.
Exactly, Simon. So we'd really like to see that what sort of which one of these would be of most interest to the audience, and it's also interesting to see if there are some regional variations that within in which parts of the world would any of these would be most interesting. And of course, it helps us with follow-up, so we can then provide some additional material in a more specified manner to the audience. It will be really interesting to see what sort of results we get from this poll. Fantastic.
Okay. So actually, we've got about 20 seconds left just for the audience. I see there's still a few people sort of deciding and looking and in progress. And just to remind everyone, while you are doing that, please do continue to submit some questions in. We've already had some great questions coming in that we're going to get to at the end of the session. So yeah, please do use the Q&A tool on the right-hand side of your screen. It shouldn't be too hard to function. If we don't get a chance to review or to answer all the questions today, I'm sure Jussi and the rest of the VTT team can actually get back to you after the presentation as well. So do bear that in mind and do submit your questions. Okay, we're just actually finalizing the poll now, Jussi. So we've got a couple of seconds, and what we're going to do is I'll post those live, and we'll be able to view them on the right-hand side of the screen like this is now. So Jussi, I don't know if you want to make a few comments. It looks a pretty even spread, to be honest, but yeah, if you want to give us your thoughts and then carry on with your presentation, that'd be great.
Actually, I was surprisingly evenly distributed. I was well, not hoping, but I was expecting a bit more variance in the answers. But this is actually a very good result in the way that all of the things that we presented so far seem to be relevant for at least some of the members of the audience. So thank you for these results, and as I said, we'll be reviewing this in more detail and getting back to you with some specific material related to these technologies. So if I carry on now, I have just a couple of more slides before our Q&A session, and I really would like to provide you with the opportunity to actually meet us face to face and live. And there are a couple of opportunities in the near future for doing that. The first opportunities are actually two trade fairs that take place coincidentally at the same time in June. The one is Powergen Europe, where all our energy people will be there. So if you're interested in the combustion, and also our experts in pyrolysis and gasification will be there, of course, too. You'll be able to meet us at the Powergen Europe in Cologne in Germany. And here it's the Hall 6. And if you're more into the pulp and paper industry and the actual looking at more business opportunities there, how to integrate pyrolysis or gasification as part of your pulp and paper industry, you can also meet us at Pulp Paper Trade Fair in Helsinki, Finland on the 3rd and 5th of June. Also, there's a third possibility which I would like to point out. So if you're actually interested in investing into power plants, what we'll actually have is a 2-day workshop for power plant investors that takes place on 23rd and 24th of September in 2014 in a city called Jyväskylä in Finland, which is about 2.5-hour drive north from Helsinki. And there you can actually see hands-on how actually low-quality fuel can be combusted at some of our pilot plants, and it's really about giving you the latest on fluidized-bed combustion technology. So if you are interested in this or if you have any other additional queries, I would like you to contact Dr. Jani Lehto, who is the head of research area for bioenergy and biofuels at VTT. So here you can see his email, jani.lehto@vtt.fi. You can also call him on his phone, which is shown here. So with this, I really thank you for being with us, and thank you also, Simon, for arranging this. And I would like to now hand over for the Q&A session.
Perfect, thank you. Okay, yeah. So as Jussi said there, let's move on to the Q&A. We have about 10 minutes now, so please do stay with us, and we're trying to get through as many questions as we can. Please do again, continue to submit your questions. Okay, so Jussi, there is still questions coming in, but if we kick off, there's one here on. It is, how much in percentage by energy of straw can be co-fired in a CFB coal boiler without severe corrosion or agglomeration?
Okay, good afternoon everybody, this is Jani Lehto speaking. So the amount of straw is actually quite limited what comes to the boilers. It quite heavily depends on whether it's a new boiler or designed to do that. So it's only a couple of tens of %, but I think there is a better option. Can you, Esa, give us a more detail?
Right, hello, I'm Esa Kurkkala and I'm responsible for our gasification R&D. So we've been working also with straw gasification, and then it's possible to gasify straw, remove alkali metals and chlorine, and then burn, co-combust this straw-derived product gas in a PC boiler or whatever type of boiler. And then we don't have these limitations for these mixing rates. So that's also excellent technology which has been demonstrated also on pilot scale.
Okay, thank you. Okay, on to the next question then that's come in. It's concerning waste gasification. Is it a possibility to gasify waste with high ash content?
Well, it depends how high the ash content is and also on the other properties of the ash. Typically, these fluidized-bed gasification processes are suitable for ash contents up to 10, maybe 15% or something like that. But of course, then we can develop other type of concepts. We can have drum kilns for first primary conversion, and then we can also develop gas cleaning and gas utilization methods for some special wastes like electronic scrap and that type of materials. But in fluidized-bed gasification, I would say that it's up to 15% maybe on the ash content.
Okay. So one here is, how about the quality of the bio oil from biomass pyrolysis? So it says, are there standards for evaluating quality of the bio oil?
Okay, actually the quality of pure pyrolysis oil that starts from biomass isn't that great. There are, I think, some severe limitations for the applicability. It means that it has a relatively low pH and relatively low heating value as such. And of course, we know that for example, the sawdust is the best possible material. But currently, there are no standards for evaluating these. We know which materials are good and which other materials are bad, but certainly, because this is relatively new business as such, all the so to say standards and norms, they are being created at the moment. So answer is there is no firm standards at the moment.
Okay. And have you looked at wastewater treatment by products as a feedstock?
Wastewater byproducts, sludges.
Yes, sorry, I'll repeat the question. Yeah, so it says, have you looked at wastewater treatment byproducts as a feedstock?
In gasification research, we have also gasified different sludges, and it's possible to make fuel gas out from sludges, even which have pretty high ash contents. But the gas quality is not very good, and it's difficult to make syngas. But for fuel gas applications to be burnt in boilers, it's possible. And also, our combustion people have been working with different co-combustion of sludges and all kind of different fuels together with other feedstocks.
Okay, thanks. And moving on, so the next question, it's broken up here, so if you need me to repeat it, please ask. But it says, can we obtain a gasification process at 450 centigrade or lower? Is it technically available? And it goes on to say, I'm interested to waste gasification in order to recover metal in waste, so I have to avoid oxidation of metal, brackets aluminium.
Well, usually if we talk about temperatures below 700 or so, we don't call it gasification, but we have staged processes where we can have a pyrolysis type of a primary conversion, then we can have thermal treatment or catalytic treatment of the product gases, and then we separate aluminium, for example, before these final conversion processes. So we have been working with that type of things, as well as the fluidized-bed gasification concept, which we developed for Corenso in early 2000, was basically operated at around 650 centigrade when we gasified the plastics, and then the aluminium was not really oxidized because there is a thin oxide layer around the aluminium particle, while 90% of the aluminium was still in metal form. So it was possible to recover aluminium. That's some technology. If you have interest for that, it is in our hands, and we can discuss with licensing and cooperation in that area. So please contact us.
Perfect, thank you. Okay, another one here is, which technology do you think is the best for tar removal downstream the gasifier? Can you please spend some or say some words on tar reforming?
Thank you. This was a very good question. I expected it. So we have developed the catalytic tar reforming for different types of gasifiers, and it's a technology where we also hold a lot of IPR, and we can license this technology to different technology suppliers and end users. So when we have catalytic reforming of tars, then we don't need to bother with wastewater treatment or low temperature removal of tars, which is very difficult. But the catalytic tar removal depends very much on the primary gasification process. So we always have to have a case-by-case development and selection of the technology. We have been working with the staged catalytic reforming, where we first take care of the heavy hydrocarbons and we avoid soot formation. Then we can go on with ordinary reforming catalysts with more or less standard technologies.
Okay, we've probably got time for sort of one or two more questions now, just to let the audience know. So next one is, I think it says there's maybe a word missing here, but it's, what is pyrolysis oil water content made by your fast pyrolysis process?
Well, actually, it depends quite a lot of the original moisture content of the feedstock that is being used, because all the water that it contains before the process will end up in the product oil. But let's say, whether depending on the moisture content of the feedstock, which might be around 8 to 10%, it varies from 20 to 30%. Hopefully, more the water it contains, the worse the quality. So hopefully between 20 and 30.
Okay, great. I think we've got time for this one last question now, then we'll have to wrap the session up. But okay, to all you guys, how are global system efficiencies being measured? Is there any comparisons between systems with and without the bio-oil production?
Okay, well, it depends quite a lot between the system. For example, for combustion systems, there is already standards how to measure the efficiencies. But basically, it's about fuel in and product out. Basically, what comes to the integration, there has been some studies even by us where we calculate the integration benefits, but most probably the integration leads to higher efficiencies and better use of the feedstock in general. So if you are still interested in that, I can find you some material. Please send an email to me. So
one advantage of this integrated pyrolysis oil production is that in this concept where we have a large CFB boiler where we take the sand and so forth, then we utilize the byproducts of pyrolysis oil also in a high efficiency boiler, basically. That generates electricity and heat with a very good efficiency. So it's much better overall concept than standalone plants would be.
Okay, thank you very much, gentlemen. Well, I guess that just leads me to say, thank you ever so much to Jussi and also Yanni and Esa for, what was a great presentation and some informative answers there. And thank you very much to VTT for sponsoring this session. The presentation slides and the webinar recording will be available at www.business-review-webinars.com shortly in the coming days. And we do look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned. And you can also follow us on Twitter at BR Webinars for daily updates, and join our LinkedIn group, Business Review Webinars. Obviously, you have the details and contact information for Yanni over at VTT on your screen, so please take a note of those. But obviously, if you want to watch the slide again or the presentation, again, that will be up shortly. So thank you once again for joining us today, and we hope you have a great evening. Bye-bye now.